almost forgot to hit record. Okay, so the first problem here is talking about the triple point of propane is 85 Kelvin, pretty low pressure, gives its critical point. The critical point is above that temperature and pressure, then we wouldn't have a discrete liquid or gas phase. We'd call that the supercritical phase above the temperature and pressure there. The normal boiling point means that 231 Kelvin is the point at which the propane has a vapor pressure of standard atmospheric pressure. So whenever a liquid reaches 760 torr, that's the pressure the atmosphere is holding the liquid into place with. So if a liquid reaches a point where that's its vapor pressure, then the vapor pressure is equal to atmospheric pressure, the substance boils. And so that's the meaning of normal. The word normal here is just the boiling point at standard atmospheric pressure. We have a 45-liter propane cylinder, contains 15 pounds of propane. Which physical state describes the sample? So we might want to make a phase diagram, but before that, let's think about the ideal gas law. Because if the substance is behaving like a gas, then we might be able to describe the pressure using the ideal gas law, get a sense of what the pressure is. We can then get a sense of what the pressure looks like to think if ideal gas behavior should make the real pressure higher or lower. And so let's calculate our pressure here. So nRT over V. So we need to do some conversions. We would imagine having somewhere a conversion for pounds to kilograms, but 1 kilogram is 2.2046 pounds. So we'd have this given somewhere to us so we can make that conversion. And so if we're calculating the moles of propane in 15 pounds, we'd use our conversion here that there's 2.2046 pounds per kilogram. 1 kilogram is 1,000 grams. Grams to moles for C3H8, which is propane. So we might go back to nomenclature for a minute. So methane is 1 carbon, ethane's 2 carbons, propane is 3 carbons, butane would be 4, then we pick up penta, hexa, hepta from there. And so then we're just saturating with hydrogens. So that's how we end up with C3H8, having a hydrogen in each of those spots. And so that molar mass would be 3 times 12.01 plus 8 times 1.008. Gives me 44.09 grams per mole of C3H8. So that gives me 154 moles. So it would seem like I'm going to have a pretty high pressure here. So I take my moles, times the ideal gas constant, times the temperature. I think it's at 45 degrees C. Oh, no, 105 degrees C. So convert that to Kelvin, of course. Then we're going to divide all this by the volume, 45 liters. So I get 106 ATM. So moles had canceled, Kelvin cancels, liter cancels, so we're just left with atmospheres. And so really high pressure. I'm going to go ahead and shut the door at this point. It's weird how I have to open the door to get people down in here. Then the hallway, oh my God, the hallway stinks. It's like Are we done with this semester yet? Just about. Okay, so 106 atmospheres. Now think about the van der Waals equation for a minute. So the van der Waals equation has a constant A that's correcting the pressure due to the sort of pressure problem, and then a B value that's correcting for intermolecular forces. And so the A term is correcting for the space occupied by matter, and then the B value is correcting for the intermolecular forces. And so intermolecular forces are going to be a big problem when we start reaching the condensation point for a liquid. So if we get close to the boiling point of propane, then that B value is going to become a larger value. So B is related to temperature, so the B value we had in a table, those are all the B values for those gases at 25 degrees C. If we want to look up a B value for a substance as we get closer to its condensation point, that B value is going to increase. It's going to have a stronger intermolecular force of attraction. The term here that's impacting our calculation is the A term. If you remember, it's like the P plus N squared A divided by something. And so this is making our actual pressure higher than what it should be. So the actual pressure would end up going higher. The B value would make the pressure go lower. So the real pressure is going to be at least 106, if not greater. And so this is just trying to show that at 105 degrees C, which is in Kelvin, 378 Kelvin, that we are above the critical temperature, and we're also above the critical pressure. And so that's why this substance here, this propane cylinder, would be best described as being a supercritical fluid. So convoluted problem. I wouldn't dwell on seeing something like this again, but the idea would be we can use the ideal gas law to calculate pressure. We can think about the true pressure. The real issue here is that the volume should be smaller. Like the volume of the container is what we're plugging in here. The matter is going to be taking up a large portion of the container. Our free space volume is going to be a lot smaller, which is going to make the actual pressure a lot higher. And so we're going to have at least a pressure of 100, if not higher, ATM. So we're well above the critical temperature and pressure. If we were to construct a phase diagram, so constructing a phase diagram, usually you would think, well, where's the triple point? The triple point is going to be the coexistence of our phases. Our critical point is here. And so our critical point here in terms of our pressure and our temperature, so this is just occurring at a temperature of 370 Kelvin, and then a pressure of 42 ATM. And then this point here, the triple point, this would be the one that's at a temperature of 85 Kelvin. And then a pressure of really low, 1.66 times 10 to the minus 9 ATM. And so just kind of we can put a phase diagram together. We don't know anything about the curve here, if it's positive or negative. We just know those 2 points. And we know a little bit about where at 1 ATM we would undergo a normal melting process and then a normal boiling process. Why do we know that? Well, 1 atmosphere is between that critical temperature. It's above the triple point pressure. So we'd undergo a normal melting and boiling for this substance. There's a couple other phase diagram questions that we'll see as we continue. We had done the second problem in this packet last time, so we'll move on to this page here. So, which member of the following pairs of liquid substances has the greatest surface tension? And so surface tension is the energy that has to be applied to a surface to break the surface. Surface tension is directly proportional to strengths of intermolecular forces. If you make the attraction stronger between the molecules in the liquid, then you have to have a stronger energy to break the surface, so hence a higher surface tension. And so let's try to think of which one's easier. Well, the first comparison is straight chain versus branch chain. And so if we count here, we have 3 CH3 groups on a carbon, so we have something that looks like this. So I have 1, 2, 3, 4, 5, 6 carbons, but with a branched chain. And then I have 1, 2, 3, 4, 5, 6 carbons connected in linear sequence. Connected in linear sequence allows adjacent molecules of this being hexane to get closer together, have a stronger intermolecular attraction as a result, a stronger ability to induce that dipole moment. So I get a stronger attractive force between the straight chain compared to the branch chain. So I get a greater surface tension for the straight chain. So anything that asks, do I get a higher boiling point for that substance that I circled? Yes. Do I get a higher enthalpy of vaporization? Yes. Anything related to intermolecular forces becomes higher for our straight chain hydrocarbon compared to the branched hydrocarbon. So the problem here is branching weakens the intermolecular forces because we're spreading out those electrons. We're not allowing the molecules to get as close together to induce a dipole moment in themselves. Okay, so the second example compares having CH2Br2 and CH3Br, where the big difference here is going to be size. So bromine's quite big, so adding a bromine atom to something like, say we had CH4. CH4, nonpolar, pretty small, that's natural gas, that's a gas at room temperature. And so if we replace with a bromine, we're going to do two things. One, we make this polar, so now we have dipole-dipole forces, and then our dispersion force is a lot higher than it would have been without the bromine there, just due to the increased size, the molar mass of bromine. So putting two bromines on the structure is even better, because I add another big atom. Bromine's molar mass is about 80 AMU, so I'm adding a lot of mass, a lot of size to the molecule, so I'm increasing the dispersion force. And I also still have dipole-dipole forces. The molecule is still polar. We have to be a little careful sometimes. If we sketch this Lewis structure, we have to make sure that we realize that that's a Lewis structure, not the molecular structure, so that the molecule is still polar. So you have to go back to tetrahedral, that the bond's really 109 degrees, certainly going to be polar, so we still have dipole-dipole forces. So we're going to get a stronger we're going to get dipole-dipole forces and then a stronger dispersion force with two bromines compared to just one. Okay, now, if you added a third, even better, right? If we had CHBr3, that boiling point would increase, the surface tension would increase. What if we went to 4? Well, going to 4 is tricky because you lose the dipole-dipole force, but then you pick up more dispersion forces. You really can't compare. It's really hard to compare something, say, 200 AMU with dipole-dipole forces versus something that's like 300 AMU without dipole-dipole forces. You really have to compare comparable molecular weights and structures when you're comparing, molecules and their properties. So we have to be a little careful sometimes when we're looking at nonpolar versus polar. We want them to be pretty similar in structure. Now, what about temperature? Does temperature strengthen or weaken intermolecular forces? It's going to weaken the intermolecular force because we're providing more energy to break those intermolecular forces. So we're going to have a stronger surface tension at the lower temperature. So you can also think as we approach a higher temperature, we're going to a higher vapor pressure. More molecules can escape with a weaker intermolecular force. So vapor pressure is the one property that goes inverse. If you strengthen intermolecular forces, it's harder for a molecule to escape into the gas phase. You lower the vapor pressure as a result. Okay, so looks like I screwed up the choices. The straight chain, 2 bromines, lower temperature water. Like there's chlorines in 2 of these choices that should be bromines. Fix that. All right, 4 is, it's a good example of a question that we had skipped in class. It's in the book. It's not one that I'm going to worry too much about, but I did want to put it here just so we can kind of see what a problem looks like. You might come across a couple of these problems on daily quizzes. What this problem here is looking at is if you have solid ethanol at a low temperature and you want to boil it at some higher temperature, then what you have to do is go through a series of raising the temperatures using the heat capacities. So you would say to go from -114 to the melting point, you have to add heat by the specific heat, CS, the MCS delta T equation from chapter 5. You'd have to then go through the melting process, which is kJs per mole. So you have to calculate how many moles there are. Not a problem I expect that you're going to see. This becomes an exercise of futility, so I don't think it's really worth our time to go through a calculation like this. When we come back to some chapter 5 review problems, we will look at maybe like an isolated part of this problem. Like if you said you wanted to go from 5-degree water to 95 degree water, well, that's just a Q is equal to MCS delta T problem. If you want to vaporize water, then we would just say, well, how much water is there? Enthalpy of vaporization is kJs per mole. We could take the moles times kJs per mole. So the most I think we'd ever see is like a chapter 5 variation of this problem where we're just going through like one isolated part of the problem, either like increasing the temperature, going through a phase transition, or going through really just a reaction with a given delta H. So we'll look at some problems like this when we get back to some chapter 5 review a little bit later. A problem like this, I wouldn't dwell on this or worry too much about a problem like this on the final. All right, 17. So we have a phase diagram for uranium hexafluoride shown. And so we have a few things that we can pick out, like the triple points above standard atmospheric pressure. It doesn't mark the critical point anywhere. So like this isn't exactly the critical point, that's not marked, but it looks like, but anyways, let's look at what the question's asking. So it's saying UF6 sublimes at atmospheric pressure. So atmospheric pressure would be 1 atmosphere. And so our solid, liquid, gas, we would get the direct transition from solid to gas at standard atmospheric pressure. So we do get sublimation at room temperature. Remember, this all has to do with the critical temperature and pressure. The critical pressure is above atmospheric pressure. And then at 80 degrees and 1.5 atmospheres, so 80 degrees here straight up, and then 1.5 atmospheres, which is probably right about here, the gas is, only the gas is present at equilibrium. At equilibrium just means that you have the sample, you let it sit there long enough so that if it was liquid, it has had a chance to vaporize. So we would indeed only have the gas present. So it's just a matter of trying to find that point on our diagram. At 80 degrees, we'd be well above 2 atmospheres to go into the liquid phase. So both statements would be true. So a sample of gas with a volume of 750 milliliters has a pressure of 756 millimeters of mercury at 30 degrees C. What pressure will the sample exert if it's compressed to 25 milliliters at minus 25 degrees C? Okay, so a few ways we can think through this problem here would be that we have some sort of a sample that has a volume. It's at some temperature, maybe it's in a water bath. Maybe there's a piston on here that I can decrease the volume and change the volume, and then the pressure will change accordingly. But then maybe I also simultaneously change the temperature. And so one way I can go about solving this problem is just to look at the ideal gas law, and that they don't tell me how many moles are in the container, but they tell me the pressure, they tell me the volume, and they tell me the temperature. So I could calculate the number of moles, and then the moles aren't changing, and so I can just use my set of conditions here, and then I can then plug into P2, V2, and our T2 where I'm going to solve for the pressure, because it's wanting to know what's the pressure after we change the volume and temperature. Now, I could also do some rearranging. Like I could rearrange that P1 V1 over T1 equals N times R, and then P2 V2 over T2 equals NR, the same gas constant and the same number of moles. So therefore, P1 V1 over T1 equals P2 V2 over T2. So I could get to this expression, plug into this expression here, and solve for my P2. That works just fine. Or I could, like I said before, I could just like isolate this part of the equation, solve for N, and then plug that in, N in down here, and then we'll solve for P2. Okay. I think it's slightly more intuitive just to do the problem in 2 steps. I think it's a little bit more intuitive just to look at the problem this way. And like this way is just fine too, but sometimes it's a little confusing on how you might get to such an equation if you needed to on an exam. So I think I'm going to just solve for N up here. I'm going to have to do a couple conversions. I'll just do them on the fly. So like when I'm solving for N, I take the pressure, 756 millimeters. I'm going to divide by 760 to go to ATM. So that's like 0.995 ATM. So I take the atmospheres times the volume. I'm going to go to liters because I'm going to use the usual gas constant. So I go times 0.750, divide by 0.08206, the gas constant, and then the temperature. I have to go to Kelvin. remember in chapter 10, everything's going to Kelvin, so that's 298 Kelvin. And so the sample has the number of moles of 0.0305 moles. Again, that's just converting to ATM, multiplying by temperature in liters, dividing by the gas constant, dividing by the temperature. And so then I can plug in down here. Let me take P2 here is going to equal nRT2 divided by V2. And I'll plug into here just to show how this works. 0.0305 moles times our gas constant times T2. Now, if you went with this approach here, you still have to convert temperature to Kelvin. Like, temperature can't go negative, or if it did, it would flip pressures to be negative. That wouldn't make any sense. And so we're going to be at 273 minus 25, so that's 248 Kelvin. Then our new volume was 0.250 liters. So I get 2.5 or 2.48 ATM. So I must have rounded something a little differently than in the problem, but 2.44 ATM is pretty close. Technically should have 2 sig figs, but the sig fig police would be mad. Okay, so this problem here, again, is coming back to the ideal gas law, just using it, applying it, either in a 2-step fashion like we did, or doing some rearranging, and then solving for P2. All right, so the next question is looking at a cylinder fitted with a movable piston that can expand against the atmosphere. The initial pressure, volume, and temperature are P1, V1, and T1. What is the new temperature of the system when the pressure is increased to 3 times its original value and the volume is decreased to 1/2 the original volume? Okay, so here we're keeping the moles constant again. This is one where if we actually go back to that P1 V1 over T1 equals P2 V2 over T2, that this problem here might be a little bit easier to solve, because what we want to know is what is the new temperature of the system. So what is T2? So if we want to solve for T2, then T2 would be equal to P2 V2 times T1 divided by P1 V1. Just doing some rearranging of this equation to solve for T2. And so the pressure is increased to 3 times its original value. So P2 is 3 times P1. So P1 cancels. And then the volume is decreased to 1/2. So 1/2 times V1 divided by V1. So V1 cancels. And so 3 times 1/2 is 3/2. And so this should be 3/2 times T1. So 1.5 times T1. That was the smell from the hallway. It smells like building, like they're doing epoxy or something somewhere. Okay, so the previous problem, just coming up with the ratios of pressure, volume, temperature, and changing them accordingly. So here we have, zoom in a little. we have a 3-liter cylinder of oxygen at 2 atmospheres. It's connected to a cylinder with 2 liters at 1 atmosphere of nitrogen. Imagine there's a valve here that's closed, and then we open the valve. And so if I open the valve, I have a high pressure here that's going to eventually and very quickly spread to the other side. And then over time, the gases are going to mix. And then so if we allow those gases to mix together and equilibrate, we might wonder like what their individual partial pressures are in the total system and what the total pressure is. And so what the question is asking for is what the partial pressure of oxygen is once the gases have mixed completely. So now one way I could look at this is that the pressure of oxygen is just going to change because it's originally 3 liters at 2 atmospheres, and the only thing that's changing is it's going to 5 liters. So we're just changing the volume. So we're just doing like a P1 V1 problem where we're changing the pressure and volume to a P2 and V2. And then NR and T are constant. So we're at constant temperature, constant number of moles, and so we're at 25 degrees C. We're not losing any gas. And so P1 V1 equals P2 V2. And so what I can do here is the pressure of oxygen after we mix would be equal to, like the V2 would be 5 liters, because we've gone from 3.0 plus 2.0 liters. So the new volume is 5 total liters. Our V1 was 3 liters. We're going to solve for P2 here, so P1 times V1. So 3 times 2 divided by 5. That gives me 1.2 atm. So the pressure of oxygen, once we equilibrate here, is 1.2 atmospheres. Weird problem. It's really just an expansion. It's just oxygen's expanding from 3 liters to 5, and then its pressure changes accordingly. It doesn't ask us for N2, but N2 does the same. N2 goes from 2 liters to 5 liters. So we start with 2 times 1, and then we divide by the new 5-liter total. So we go to 0.4 atm of N2. So the partial pressure of nitrogen after the expansion is 0.4 atm. Then the total pressure is 1.6 atm. So the total pressure is just the sum of the two partial pressures. This doesn't really relate to the problem, but we might remember if we had the mole fraction of one of the components of a mixture times the total pressure, that gives us the partial pressure of one of the components. And so since a quarter of the pressure is nitrogen, a quarter of the mole. So nitrogen's moles would be a quarter of the moles, oxygen's would be 3/4 of the moles. So we can come up with problems where we relate the mole fraction. And so for like nitrogen, if the partial pressure is 0.4, the total pressure is 1.6, so the xi has to be 0.25. So that's how the mole fraction of N2, we can see here the x of N2 would be 0.25. And the mole fraction of O2 would be 0.75. So if we had a bunch of gases in a tire, car tire, let's say, and there's a pinhole in the tire, the gas that would diffuse the fastest is the one with the highest velocity. The highest velocity, if we think of like 3RT divided by molar mass, square root of this to calculate our velocity, this is the VRMS velocity, that the lower the molar mass, the higher the velocity. And so the lighter the particle, the higher the velocity, so the particle that would escape the fastest at room temperature would be helium, of these 4 choices, just because it has the lowest molar mass. So 4 grams per mole versus oxygen 32, water's 18, CH4 is about 16 AMU, so helium's the lightest, escapes with the fastest rate. So which of the following, lithium, diamond, oxygen, neon, has the greatest melting point? This is kind of a tricky question, but this is getting at, in chapter 12, we were talking about some different types of solids. So this is a metallic solid. This would be a covalent network solid. Oxygen and neon would be molecular solids. The molecular solids would have the lowest melting points, so these would have the lowest. So the highest would be between A and B. If we go back to O2 and neon would probably be lower because it has a lower molar mass, a single atom. So if we're ranking these, neon's probably the lowest, then O2 is probably next. Now, lithium versus carbon's a little tricky, but it kind of comes down to covalent networks were generally stronger bonds. So I don't know. I'd probably have lithium then carbon diamond, just because of how strong that carbon diamond was in terms of its structure. If you remember, its melting point, I think we mentioned, was over 2,500 degrees C. Lithium turns out, I think it's only like 200 degrees C melting point. But just a couple examples, just something to think about the different types of solids. So if we're asked a question like this, we don't just want to look at and say, well, oxygen's the biggest, it has to be oxygen. I've seen that before on the test where we default go to oxygen being bigger, has to be higher. We know diamond is a solid at room temperature. We know lithium's a solid at room temperature. We're probably trying to think of which structure is a stronger structure. It's that covalent network structure. So describe NaCl solid. Is it crystalline or is it amorphous? So if you remember, amorphous would mean that there's no repeating pattern. We saw that our ionic solids tend to form a crystal structure. So they tend to form with a specific repeating pattern. And so our ionic solids are crystalline in their appearance. Molecular solids would usually be amorphous. Other things that would be amorphous are just things that are, like if you knew the appearance was more dull. A crystal would be brighter in appearance, maybe more colorful, if you knew something about the appearance. So is NaCl molecular, covalent network, polymeric, or ionic solid? It's a pretty easy question. It's, of course, an ionic solid. So a molecular solid would be something that exists as a molecule, like water, CO2. A covalent network would be something like carbon, silicon, usually something in more the metalloid area of the periodic table. Cannot spell. It's bad when you can't spell and write. A polymeric solid would be probably something hard to pick out. Like we could think of a plastic or an example of a polymer. In terms of a formula, it's something with a repeating unit like CH2. CH2 is our simplest plastic. So something like this would, the N here, repeating up to like 1 million plus times would be an example of a polymer. Which of the terms would describe carbon in its diamond form. Even if you had carbon in its graphite form, it would be the same answer. It would be covalent network. And the idea of covalent network is we have three-dimensional arrays of covalent bonds in the structure of carbon, diamond giving it a really strong structure, really high melting point. An example of a molecular solid, we've given a couple already, like above, like O2, if it's a solid, it has to be really low temperature, water and ice form, dry ice, CO2. So anything that just exists as a molecule in its solid form is a molecular solid. And what holds a molecular solid together are intermolecular forces. What hold covalent network solids together are covalent bonds. What hold polymers together are covalent bonds through the structure and then dispersion forces between the strands of the polymer. What holds ionic solids together are electrostatic forces of attraction, lattice energies. So melting point of ionic solids are often proportional to their lattice energies. So which compound below would you predict to have the greatest melting point? So which ones can we rule out? So I'm seeing +2 -2s, +1 -1, +1 -1, +2 -1. So I can rule out the -1 +1s because they have lower magnitudes of charge. I'll roll out the +2 -1 as well for calcium fluoride. So I'm choosing between calcium sulfide and MgO because these are both 2 + 2 minuses. So the higher the charge, the stronger the attractive force between the ions. But then the smaller the ions, the better. The smaller the ions, the greater the attractive force. This just comes back to a Q1, Q2 divided by D. Closer together gives us a greater energy of electrostatic attraction. So MgO, smaller ions, just because magnesium's higher up on the chart, smaller than calcium, oxide smaller than sulfide. All right, so we've reached a point where we've kind of gone through most of the chapter. I mentioned we'd look at chapter 10 to 12 first in the review, and then we'd kind of go. This is going to be fairly well scattered between chapters 1 through 9. So it looks like we're starting here in chapter 9 with this problem here. So looking at MO theory, we have our diagrams for boron, carbon, nitrogen, their ions here, oxygen, fluorine, neon, their ions here. Remember, these are our 2s electrons, or what those are representing. These are representing the 2p sets. And then our orbitals would be sigma 2s star, pi 2p, sigma 2p, pi star 2p, sigma star 2p. And the opposite here, we're just flipping here this into a sigma 2p and a pi 2p. Otherwise, the same order of orbitals. Okay, so according to MO theory, let's look at the bond order of C2 with a 2 plus charge, and then O2 with a minus 2 charge. So C2 with the 2 plus would be 2 times 4, and then minus 2 electrons for the 2 plus. That only has 6 total electrons. So for C2, 2 plus, I'm over here for C2 and its ions, and I'm putting 2, 4, 6 electrons into place. And so I could have started here too by putting C plus and C plus coming together to form C2, 2 plus in the middle, and carbon with a positive charge would look like this, meaning 2s2, 2p2 for carbon, take 1 away for carbon plus. I don't necessarily have to put these electrons in over here. It might be helpful to think about it, but it's those electrons interacting with each other. So I get bonding, anti-bonding orbital. So I only have 2 net bonding electrons. So I have 4 bonding electrons minus 2 anti-bonding divided by 2. So I have a bond order of 1. So a single bond between C2, the 2 carbons, and C2, 2 plus. So if I'm sketching a Lewis structure, probably something like this, something like that. Each carbon should have 4 electrons, right, for a neutral charge, and each one has 3, hence the positive formal charges. Okay, so C2, 2 plus, bond order of 1, and then O2 with a minus charge, or O2 with a 2 minus charge would be like an O minus and an O minus. And so that would be 2s2. This is oxygen, so that's oxygen minus. So I just have an extra electron over what would have been oxygen. And then I have a total of 2 times 6 plus 2. That's 14 electrons going in, so 2, 4, 6, 8, 10, 12, 14. So I filled through the pi star 2p orbital. So again, making sure these are my anti-bonding electrons, and then these are my bonding electrons. So my bond order for O2, 2 minus will be a half, 8 bonding, 6 anti-bonding. So that gives me a bond order of 1 as well for O2, 2 minus, like C2, 2 plus. Now, if I'm looking at a Lewis structure here, again, single bond, and then probably something like this. So 2, 4, 6, 8, 10, 12 non-bonding electrons, and then the 2 bonding electrons for a total of 14 electrons being distributed, minus charges on the 2 O's. Looks like answer A. So is C2, 2 plus paramagnetic? So paramagnetic is the active being drawn into a magnetic field. And so C2, 2 plus would be because we have 2 unpaired electrons. So at least 1 unpaired electron is paramagnetic. So C2, 2 plus is paramagnetic. And then B2 would also have 6 electrons, would have the same type of diagram as C2, 2 plus, would also be paramagnetic. So both 1 and 2, both C22 plus B2, both have 6 electrons, both have the same type of diagram. Lewis structure of SO2. Now, sometimes we see a question like this. Sometimes we look at the choices, and if you start looking through the choices, you might be like, oh, this looks pretty good. It looks like CO2, but it's not right. But you may also, like, if you're just evaluating the Lewis structures, you might have a little bit of a hard time. You might even think this one looks pretty good because it's like, okay, sulfur has an octet, the oxygens have an octet. Why would that one be wrong? Well, let's just go back to the rule. 6 times 3 here, 18 electrons. Applying our rules for Lewis structure, we'd start here, here. And the reason why we do that is just to make sure that we have 2 leftover electrons that have to go onto the central atom. If we don't do this sometimes, we may not get the proper number of electrons on the sulfur atom. And so then here at this point, the question is, well, what's our charge on sulfur? Our charge right now would be 2 plus. And so then we can draw and make a double bond this way. And so we can make a double bond here. And that would be one of our valid Lewis structures that looks like this one here. And then we could equivalently have put the Lewis structure, left it here and put the double bond here and just had S double bond O, single bond O over here. That's the equivalent yet different Lewis structure so that we have resonance going on in this molecule. So this would be another choice for a Lewis structure. And then the only other choice we could have had is this one here, which is not one of the choices. So if you notice, that's not one of the choices above. So this one here is not necessarily a wrong Lewis structure. This is the one that minimizes magnitudes of formal charge. The formal charge here is still +1, negative on the other oxygen. Let me clearly show the Lewis structure. So I have minus on the O with a single bond, 0 on the O with a double bond, and then it's going to resonate. The molecule really never has a double or a single. It always has like a 3/2 type bond. It always has the resonance going on. It really always looks something like this, where this looks like a 3/2 bond. Why 3/2? Well, I have 1, 2, 3 pairs of electrons spread across the 2 covalent bonds. Okay, so this Lewis structure would be best, and then the other one that might be best isn't shown. So then this one here is wrong because sulfur doesn't have the pair of electrons that it should have. What is the formal charge of phosphorus in the Lewis structure of phosphate, where all atoms obey the octet rule? And so I would have 5 plus 4 times 6 plus 3. So that's 32 total electrons. So I'm going to have a central phosphorus, 4 oxygens, octets around the O's, and that's all 32 electrons. So none left over for phosphorus. And so this would be our best Lewis structure of phosphorus because I have phosphorus here with 8 electrons around it. So its octets being satisfied. It does have a positive formal charge. Has a positive formal charge because it only has 1, 2, 3, 4 electrons closest to it. Phosphorus should have 5 electrons for a neutral charge. It only has 4, so it has a net positive charge in terms of its formal charge, so +1. Number 11, which statement is true about the resonance in the structure of ozone, where 2 oxygens are connected to a central oxygen atom? This is a lot like the SO3 structure, where we have this here as one of the Lewis structures, and then the other Lewis structure is the one where we have the double bond on the other side. And so the act of resonance is the electron pairs are always distributing themselves across the 2 sets of bonds at all times. So it really looks something like the composite here. And so it really looks more like a 3/2 bond. Let's look at the choices. Ozone contains 2 oxygen bonds of it should be equal length, not different length. So 2 bonds of equal length. And then the oxygen atoms should have a formal charge of about 1/2. Why 1/2? Well, it's either 0 or -1, -1 or 0, so this should average out to -1/2, -1/2. So the formal charge of each of the O's is about -1/2. The bond orders would be about 3/2 if we were asked about that. I don't think we tend to ask about the charges too often. I've talked maybe a little bit about how the charges balance out, but I don't think you'll see something like this asked. But you can think about the charges, you can think about the bond lengths equalizing in length, you can think about this being a fact that takes place at all times. It's not a back and forth. This was on the midterm. One of the questions a lot of people missed was, is residence a back and forth, or is it an at all times effect? It's an at all times effect, that it looks like the composite. So it's never A, it's never B, just because we sketch those structures. So we have to just understand or appreciate that whenever we sketch a Lewis structure and then we realize, oh, I can sketch this other Lewis structure that's equivalent yet different, then it's never the one or the other, it's always the blend of the two. Now, the reason why it's a blend of the two is the delocalization of orbitals, if you recall from chapter 9. You can sketch these orbitals that a single orbital can delocalize those electrons at all times. Okay, so let's go to Vesper theory. What's the electron domain geometry, molecular geometry of Cl(O2)-? Well, we have 3 atoms, so in terms of the molecular geometry should either be linear or bent. So if I look through the choices here, like trigonal planar doesn't make any sense. So we can rule out answer B right off the bat, because with 3 atoms, it's either linear or bent. And so for Cl, 2 oxygens, let's count our electrons, 7 for chlorine, 2 times 6 for the oxygens, plus 1 for the negative charge. That's 20 total electrons. And so octets around the O's is 16 electrons, 4 leftover electrons onto the chlorine atom. And so at this point here, chlorine would have a formal charge, should have 7 electrons for neutral charge. It has 1, 2, 3, 4, 5, 6 electrons closest to it, so plus 1. I could play around with double bonds, right? We could make a double bond, we can then resonate the electrons, but if I just stay here, or we just recognize it doesn't really matter if this is single or double bond, because it's still one domain, whether it's single or double. So I have 1 domain here, I have 2 domains here, 3 and 4, I have 4 total domains. So that's tetrahedral electron domain geometry. So I have tetrahedral electron domain. So if I'm thinking of the structure, central chlorine, oxygen, oxygen here, and then electron pairs sticking straight out of the page. So I have electron pairs sticking out in the tetrahedron direction. Hard to sketch, slightly easier to sketch if we put the electron pairs. If I want to re-sketch this, I might put the chlorine in the same spot, but put the electron pairs here and here, and then I can wedge out the oxygens, maybe a little bit easier to see the structure this way. And so the structure here clearly going to be bent, just like water, just like a lot of molecules. And so it's going to be tetrahedral and bent. So to be linear, we're either 2 domains, both bonding, no electron pairs in the central atom, or we actually need 3 electron pairs in the central atom. If you remember, the only other structure that goes bent is trigonal bipyramidal domain, with 3 of those domains being bonding, so like xenon F2. If you remember, xenon F2 was linear, where we had 3 domains on xenon. Okay, so 49 bond angles. Erase a little. Whoops. So what are the approximate bond angles of A, B, and C in the structure below? And so for the bond angle about A, all I'm picking up on here is I have 1, 2, 3, 4 domains. So that's tetrahedral. That's sp3. So that nitrogen would be sp3 if we go to hybrid orbital theory. So the bond angle for A should be that of tetrahedral, so about 109.5. B is also tetrahedral, or the central atom here is tetrahedral sp3, so that should also be 109.5. Then angle C is trigonal planar, So C should be 120 because we have 1, 2, 3 domains, so that's trigonal planar. So 120 degrees for C. So 109.5, 109.5, and 120. So consider the molecules below, which ones are polar. So if I have BRF, this diatomic molecule is really easy. Just if you have a difference of electronegativity, you have a polar molecule. I like to think if you have NOF and then chlorine, maybe sulfur, and maybe bromine, these are the most electronegative atoms. If you have those atoms paired up with anything but themselves, the bond's certainly going to be polar. Once you get to the case of having like C and H don't differ in electronegativity by much because neither atom's very electronegative, so the difference is pretty small. It's like a CH bond. If I see a hydrocarbon, I'm not even worried about how it's connected. It's just going to be nonpolar. Okay, so BRF certainly going to be polar. BRF3, this comes down to a structure. If this is trigonal planar, then it would be nonpolar. BRF3, I have central bromine, 3 fluorines. I have 7 times 4, 28 electrons to distribute. There's 24 around the Fs. So the 4 electrons left over. Go on to the bromine atom. And so then I just go back to bromine being described with 5 total domains, 2 non-bonding. What's the shape? Well, the shape is the one I've drawn. It's T-shaped. So it really does take this type of shape here. And then T-shaped, we have a negative charge on the bottom, not matched on the top. So this molecule here is certainly going to be polar. BRF5, again, the thought for BRF5 would be if we somehow fill in trigonal bipyramidal, then it would be nonpolar. But let's double check. 7 times 6 is 42 electrons, so it's probably not going to be trigonal bipyramidal. So for BRF5, central bromine, 5 fluorines. I'm alluding to the structure, of course, because for each of the fluorines, we have 8 electrons. There's 5 of them. So I have 2 electrons left over to go on to bromine. So bromine ends up being square pyramidal. If we wanted to name the shape, we get a square pyramid structure. And then square pyramid, I have negative charge here that's not balanced on the top end of the molecule. This molecule here is certainly going to be polar. So all 3 here are polar. But we just have to go back to their molecular geometries. I can't look at the Lewis structure and tell. I have to sketch a Lewis structure and then put together the molecular geometry shape, picture that shape. In each of the cases, I was sketching the shape kind of ahead of time, kind of alluding to what the structure was going to be. So I have a structure that looks T-shaped and square pyramidal in each of those already. Let me just see if these questions here, I don't think either one of these take 2 minutes. So let's go ahead and stop here so we get one more data review in class on Wednesday. So we'll review on Wednesday. I have some extra office hours I posted previously on this page. I sent an announcement out with those. So I would go today till 11, usually just till 10:30, but till 11 today, 9:15 to 11. Same thing Wednesday and a couple extra Thursday and Friday. So stop by this week if you have questions.